Well, welcome back, and we are going to finish the preparation for examination number 2 by going into chapter 4. So this is the third part of 3 videos for that particular section. So when we were last here, we finished up probability, and in chapter 4, now we start to talk about testing and hypothesis testing. And in our first question here, we talk about a difference of a type 1 and a type 2 error. So remember that what happens in a type 1 error is that we act on something. We do something. However, though, in that action, though, we have falsified what we've done because really nothing was happening at all. So when we look at a type 1 error, what we're looking at is we're looking at we rejected or chose to reject a null hypothesis when in fact the null hypothesis was true. We can equate this to we basically convicted somebody who was innocent of something. Nothing was going on, the innocent part here, but yet we acted on a conviction. So we took the alternative. We chose to not believe the null hypothesis in a type 1 error. A type 2 error is just the opposite of that. If up here we rejected a null based on and nothing was going on, well, the controversy of that is that we did not reject something. We failed to act upon something. And when in fact, the null hypothesis was false. So something was happening, but we failed to act upon it. We call this the letting a guilty person go. So we let a guilty person go because we didn't believe something was going on when in fact they were guilty. Both have their own ramifications when we do something, and how we test, or are we more concerned with making a type 1 error or a type 2 error, will come about as we go through some problems. In number 25, it says the definition of a p-value. So the p-value equates itself to the actual rejection or the fail to reject up here, because a p-value is what quantifies me actually doing that rejection. And it says the definition of a p-value. Well, the true definition of a p-value is that it is the probability, because it's the area under the curve, when the null hypothesis is true, of obtaining, and all this means right here, this null hypothesis true means it's centered up at where we want it to be, at the null hypothesis, of obtaining a sample as extreme or more extreme than the observed sample. And in a basic notation of that, again, the null hypothesis is true. My CI, my confidence interval level, extremes, so maybe 95%, 98%, 99%, that really doesn't matter, but here is my cutoffs for my CI. And this p-value is the area of getting an value which is as extreme or more extreme, and I'm using a right side tail test example here, as extreme or more extreme than the observed sample. So here's the number we got, and these are all the p-values that were more extreme or at least as extreme as that p-hat value that I observed, the observed statistic, okay? In the situation below, 26 and 27, describe what it means in the context. So context of the type 1 and type 2. Okay, so we're trying to test to see if a well-known company is lying in its advertising. If there is evidence that the company is lying, then the Federal Trade Commission will file a lawsuit. So the first one, making a type 1 error. Now, remember, just from what we just discovered, that a type 1 error is that we reject a null hypothesis, but the null hypothesis is actually true. So what we're looking to go down through here and find is we're looking to, we formulated action when we should not have formulated action. So if we go down through here and we sue a company for lying, well, we did action, but there was action to be had, so that's not it. We let the company off a hook. We failed to act. That's not what we're looking for. We're acting on something. Sue a company. That's an action we took, and we did it, but they are actually not lying. We took an action when nothing was going on. We made a type 1 error. We acted on H of O when H of O was actually true. Now, a type 2 is just the opposite. We're going to fail to take action when we should have taken action. So we're going to go down and find the one that says fail to take action. Let the company off the hook. So we didn't do anything, but they were actually lying about their advertising. Hope that clarifies your type 1 and your type 2s. Law often uses a type 1 and a type 2 error for analysis of casework. If the significance level is 5%, which p-value provides more evidence against H sub O? First of all, the only evidences are evidences which are smaller than 5%. Okay? That's the only ones that are going to happen. So for instance, over here, we have 6.5%. 6.5% would be no evidence against a p-value of 5% because it's already greater than that. So we want the ones which are the smallest decimals that are less than 5%. Well, 0.0075 is my smallest value, and my smallest value is the most significant against a 5%. It says the hypothesis H of O, P, H of O is P sub 0, and H of A is less than 0.8. The sample outcome based on 10 observations and a p hat, there's my sample, of 0.7, and the randomized statistic to be calculated for p hat. The p-value for this test was found to be 0.322. That's pretty large. It's much larger than any sample that or any p-value that we've seen so far. If the test was performed correctly, where should the randomized distribution be centered? Okay, well, the question doesn't really say about rejection. It doesn't. All it wants to know is where's it going to be centered at? Well, it's going to be centered at H sub O. You go to H sub O, and there's your answer for centering. If it asks you which way it's going to be tailed, it's going to be tailed to the left because it's a less than tail. If it asks you what statistic you're measuring 0.07, and you're measuring all the things to the left of 0.7, and there was a high probability of that, so there's a lot of data values in that curve. An article published in the Canadian Journal of Zoology presented methods for estimating the percentage of body fat of North American porcupines. The method was illustrated with a sample of n equal 25 porcupines based on that sample of 95% bootstrap confidence interval level for the average body fat percentage for porcupines from 17.4 to 25.8. Which of the following null hypotheses would reject based on the confidence interval level? All right, well, okay. So my CI is here, and these are my null hypotheses values. So first of all, 18.6 is in between these numbers. Do not reject. 20 is in between these new numbers. Do not reject. 22.9 is in between these two numbers. Do not reject. 26.6 is outside of the CI. This is my rejection. We reject the null. We reject based on the fact that the null is outside of the CI. We're not looking for the alternative. We're looking to see if the null hypothesis is actually within inside of what we feel the confidence interval level should be. If the null hypothesis is not within inside of the confidence interval level, then we reject based on that. Move this down a little bit so we can see it, all of it. It says the following randomization distribution given for U sub S equals U sub 1 versus S not equal to 1. Okay, so these are mu values, and we're finding a p value. So first of all, we have a lot of information. We have the randomized dot plot. We have the original sample. We have the randomization sample for the dot that was currently placed over here. We have a two-tailed test. I know it's a two-tailed because it's a not equal. So a two-tailed means we have to encompass both this and this area. We're looking for all the area over on this side and all the area over on this side from the statistics themselves. So we take the area that's given here, 0.031, and we multiply it by 2 to give us a value of 0.062. If this was a right side test, then it would just be the area that I see to the right. If it were a left side tail test, it would just be the area to the left. A statistical test is conducted to see if there's any evidence that the production of U.S. adults who own tablet computers is greater, right side tail test, than 0.5. Use the following possible sample results to determine of the sample the most significant evidence. Okay, so the first thing I do here is I take my 200 successes and I divide them by my 450 claims and I get 0.44. And then I do the same thing, 0.78, and the same thing, 0.66, and the same thing, 0.40. Then remember, so I have a 0.44, a 0.78, a 0.66, and a 0.40, small to big. The question is, which one is greater than 0.05? So when I look at these values, I'm looking to see which one is the most extreme to the right-hand side of 0.50. The one which is largest to the most extreme to the right-hand side is 0.78. So sample B is my correct analogy. Excuse me. Number 33. True false. So I love true false. Here we go. A statistical test uses data from a sample to assess a claim about a population. Absolutely true. A large p-value, the greater the evidence against H of O. Absolutely false. The smaller the p-value, the greater the evidence. We want a very, very small area because we want to show that what we have found is unusual. A p-value should be between 0 and 1 inclusive. Yes. You never will go over 1 because it's a percentage, and you will never go less than 0. It's a percentage. For a significance level of alpha 0.05, the decision for a p-value of 0.004 is to reject H of O. And that's true because 0.004 is less than 0.05. If this is less than the alpha, then you reject based on the p-value. Do not reject H of O is the same as accepting H of O. False. The only thing we have found is we did not reject H of O. Statistical significance is not the same as practical significance. That's true. They are not the same thing. To be statistically sound does not mean that we can practically put that into place. Replication of a study with similar conclusions gains credibility. Absolutely true. The more times you can do the test and the more times you can get conclusions which are similar, the more credibility you have. The center of the randomization distribution is around the sample statistic. Now, the sample statistic is the bootstrap. If a 95% CI misses the parameter in H of O, then a two-tailed test should reject H of O at alpha 5%. That's absolutely true. We just did that a second ago. If my H of O is not inside of my CI, then I should reject H of O. Now, notice that the 95% has an alpha of 5%. Those have to counter each other and add up to be 100. So if this is 98, this has to be 2. The farther out in the tail the sample statistic is, the smaller the p-value will be. Absolutely true. The further you move out on the tail, the less likely it is to happen, the smaller the area of probability. And the last one, confidence interval levels are for estimating the value of a parameter, while the hypothesis test whether, hard with test and test whether the data provides evidence against a specific hypothesized value. And that's absolutely true. A CI gives us a parameter, a width of something happening, whereas a test actually looks for actual data, p-value, that we can utilize to either reject or fail to reject a null hypothesis. 34. Indicate the analysis involves a test. If yes, then what's the population parameter and the interest? Okay, so first of all, polling 800 people in a large community to determine if there is evidence for a claim that the percentage of people in the community living in a molehill is greater than 14%. Well, yes, we're taking 800 people, so we are actually doing a statistical test, and we're trying to get something greater than 14%. So our population parameter is going to be P equal 0.14. That's my H sub O. And my H sub A would be P greater than, evidence claim that percent of people is greater. P greater than 0.14. The second one, utilizing the census of a community to determine if there's evidence for a claim that there's same thing is happening. Well, the census is everybody. So no, there's no statistical test here. You have to take a certain group of people, you have to measure them, you have to get a p-hat value from that after establishing an H of O and an H of A. If you're not physically performing a test with a certain number of people, you don't have a stat test. Use the following questions. Match the p-value with the most appropriate conclusions. Okay, so here we go. Let's read this first. So the evidence against the null and in favor of the tolerant is very strong. So you see that word's very strong. You're looking for something very, very small. B right here, 0.0001. It's the smallest value I have, and it's very strong. The result in the significance level at 5%, but not 1%. Okay, that means it's smaller than 0.05, but it is not smaller than 0.01. We go to D right here, smaller than 0.05, but not smaller than 0.01. Here's my second one. There is no evidence to support the claim. Okay, well, what would tell me no evidence? Well, no evidence means you're bigger than 5%. The only number here bigger than 5% is right here, 0.608. The evidence against the null is significant, but only at 10%. So it is smaller than 0.1, but it's not smaller than 0.05. Smaller than 0.1, but not smaller than 0.05. Just go down through those as I just did and just find your numbers from there. In 39, we're looking for errors here. What's wrong with these valid or not valid statements? So, first of all, first one's not valid based on the fact it used a statistic instead of a parameter. You always use a parameter in your H sub O and H sub A. Second one, also not valid because, why? It didn't use an equal sign. H sub O always uses an equal sign. So far we have to have a parameter and we have to have an equal sign. Equal sign, parameter, we're good. So in the second one, it's a good one. Next hypothesis. It looks okay because we have a p-value here of 30 and a p-value here, and it looks all right, and it's got an equal sign. However, proportions are never greater than 1. So 30 makes this thing invalid. Now, if that were a row value would also go out because remember that an R value is never greater than either. So in a P or a row, this is never going to happen. The only way this could happen would be a mu value. Next one, we have a hypothesis value, so we are greater than here and right here. We can't have an equal on this one too, because if we're equal here and equal here, then they're the same thing. The next one, P1 minus P2 is 0, P1 minus P2 is not 0, that's good. Here we go, we got a row value that's greater than 1, can't do that. Row values and p-values cannot be greater than 1. And in the last one, the hypotheses P1, P2, P1 minus P2, I can't have a 0.5 over here. So this is a no also. Lots of no's. We only had 1, 2 yeses. Probably means something. Number 40. I have to reorganize a little bit there. So we're testing this, or we're identifying if this is a CI confidence interval, if this is a hypothesis test, or if this is just not statistically relevant at all. So the question is, what proportion of people using a public restroom wash their hands after going to the bathroom? Okay, well, first of all, there's no test being involved. So at most, we're looking for a range of people who actually do this, and it's a CI. In 2010, the President of the United States U.S. Senate voted to confirm Elon Kagan as a member of the Supreme Court. Well, we're just counting something here. There's no test, there's no interval, there's no anything. It's just going to be a count. So no statistical relevance. Do the majority of adults riding a bicycle wear a helmet? Okay, well, we're going to go. This is not, it says do the majority. So we're testing something for validity. And if we're testing for something for validity, we have a hypothetical or a hypothesis test. On average, how much more do adults who play sports in high school than adults who did not play high school? So it's a range. It's a range of numbers. If you can find a range that you're measuring, it's a CI. What is the average daily intake for 20-year-old males? Okay, well, again, it's a range. And if I can find a range, I have found a CI. The only one that tested something was this one here. We were asking, does this happen? So do the majority. Well, the majority, remember, means 50% or greater. So in this one, P sub O would have been 0.5, and H sub A would have been P greater than 0.5. In 41. So let mu be the average amount of sleep that a college student has per night. Data was collected on the sample. 6.7 was the data sample. A bootstrap distribution is generated with interval of mu. The randomization distribution is generated to see the data provides evidence that it's greater than 7.0. Which one of these is a bootstrap? Okay, well, a bootstrap centers itself up around the data statistic. So we have to find the one that has a middle of 6.7, and that's the one that's our bootstrap. If I go down to the second question, I assume it's going to be very similar, but the question is probably going to change and ask us something besides the bootstrap. So we go through the reading. And I'll let you read it. And we have 152 out of 218. We know that we're evidence, which is P is greater than 1/2. That's what we're measuring. Provide evidence P is greater than 1/2. Which of these is the randomized distribution? Well, remember the randomized distribution is not centered up at the test statistic. It's centered up at the null hypothesis. Since we're measuring greater than 1/2, that means the null hypothesis is 1/2, and we're measuring from the center. The randomized distribution is the same as is the distribution for the null hypothesis, and the null is always the center. 43, kind of bring it all together here. Given that H sub O is 0.4, that's our center, versus right side tail test greater than 0.4, 4 possible statistics along with 4 possible p-values are given. Match the statistic to their p-value. Okay, so let's go, let's grab the first one. So first of all, my center is 0.4. I'm going to be at 0.3. Okay, now think about this. 0.3 and going this way. From the middle, this way is 50%. From here to here is 50%. So I need something bigger than 50% because I need all of this and I need 50% right over here. So if I look at A, the one that's going to give me the largest p-value, this is not bigger than 50. This is not bigger than 50. That is not bigger than 50. That's bigger than 50. So A has to go down here. I go to the next one, 42%. Or excuse me, a statistic of 0.42. So I go find 0.42, which is a little bit to the right, just barely to the right of the center. Remember what I said, the center is 50%. So it's just a little smidge smaller than 50%. So if I go look at that one right there looks good because I'm not going to go with that little bitty one and I'm not going to go at 10%. I'm going to use this one right here, B. P hat of 0.5. So go find 0.5. I moved over quite a bit. So now really the area I'm talking about is over here. Clearly not 50%, but also probably not real small because this over here is probably about 10 or 15%. So I go to what's left for C. My choices are 6%. My choices are 15%. Well, I'm going to go with 15% because I think definitely it's not 0.6%. Then if I go to D, 0.65, I mean, that thing is way over here. There is a very small amount of area over here. I want the smallest amount of area up here, and this is the smallest amount of area up here. So I kind of use the process of elimination, if you will, to go through the largest area, the smallest area, and then fit the stuff in between. And I'm always gauging against 50%. Look at the center, take 50%. Do you need more than 50 or less than 50, and how close to that 50? In a hypothesis test, H sub O, the mu value is 12, and it's less than 12 for H sub A. We have a sample statistic, n equal 45 with X bar equal to 10.2. There's my sample statistic. This is my number of samples. What do we require about the method to produce the sample? Well, all we need to know is where's the center, and the center is at 12. We will center everything up at 12. Where will the randomized distribution be centered? Same place, 12. So we need to know mu is 12, and we need to center at 12. What will we look for in the randomized distribution? What we will look for is how extreme 10.2 is. We're going to measure the probability that 10.2 happens when 12 is the center. In a hypothesis test for mu1 equal mu2, and we're testing mu1 is greater than mu2, we have a sample of x1 is 26 and x2 is 21. What do we require to know about this? Well, what we require to know is where the center is, and the center is mu1 minus mu2, or mu1 minus mu2 equals 0. We need that center. And second question comes in and says, well, where are you going to center it? We're going to center it at 0. If I subtract a mu2 from a mu1, then I'm equal to 0, and I'm going to center all null hypotheses at 0. What do we look for in the randomized distribution? Okay, well, now this one could get tricky. We don't look for 26 and we don't look for 21 because remember, mu1 minus mu2. Mu1 minus mu2 is 5. We are going to look to see how extreme 5 is. This is a difference in means, and our statistic comes from the difference in means. So I got that by taking x1 minus x2, and that was equal to 5, and that's the extremity that I am looking for. Without finding p-values on StatKey, which sample has the strongest evidence for H sub O, which is 0.5, and which one has the strongest evidence against 0.5 using p-hat at 0.58? All of these have 0.58. So it's like, what the heck? Which one am I going to use? Well, this one had an n value of 50. I can see that because of the denominator. This one had an n value of 5,000, and this one had an n value of 500. Remember, more n values, more statistical relevance. Always go with the greatest number of n values. It is believed that sunlight offers some protection against multiple sclerosis. All mice were injected with proteins known to induce a mouse form of MS. Researchers randomly assigned mice to either group control vitamin D or UV light. Scientists found that mice exposed to UV were significantly less. So UV was significant and to compare to the control group, but vitamin D did not see as good of a likelihood. Okay. One p-value was 0.472 and the other was 0.002. Which one goes with which? The significant test, the UV light, would take the smaller of the p-values because it was significant. The vitamin D that didn't seem to do anything would take the very high p-value because we would never reject something with a 0.472. We would reject a 0.002 even based on a 1% alpha. In the provided figure, mu is 100 and H of A is greater than 100, so it's a right-side tail test. The p-value for the mean sample, 118. Remember, this is 108, this is 112. 118 is out here somewhere. Would it be about 4%, 45%, 75%, or something very, very small? Always an extremity out there is going to be a very small p-value. Number 49, I'm going to let you read it. It's down at the bottom. It talks about owning a cat and the mental illness of toxoplasmosis. Okay, I got to flip over my page so I can get to it. It says for the study and to calculate the relevance of proportions to the cases, those schizophrenia and those owned by those who did not. And this was actually inside of your homework. You would have saw this in Wiley Plus. It says round your answer to 3 decimals, and it wants p-hat1 minus p-hat2. Okay, so the first thing I had to do is I had to go back inside of the question, and mine didn't print out real great. But my first one was 136 out of 262 had were measured for the disease. That was my p-hat1. And of those who were not, it was 220 out of 522. When I subtracted those two values, I got 0.098. Okay. Now, question would be, and I got to move around a little bit here. I'm sorry that I've got a lot of paperwork in my way and I can't really get to it all. So the question becomes in the next one, 49, state H of O, and state H of A, and what we're going to do here. So when we talk about finding H of O, we're talking about H of O, nothing going on. There is no difference between P1 and P2. If we're doing H of A, we want to see that those with this value are greater than those with this value. So we want P sub 1 to be greater than P sub 2. Okay, so if H sub O is true, H sub O, then P1 is equal to P2. And in H sub A, P1 is greater than P2. In other words, if I subtract these, this one is equal to 0, and this one will be greater than 0, or some larger value. Do you think, okay, so then we run our hypothetical test, and here it is for you. Show you the nice picture. And you can see that 0.98 that I ran right there, I can find that right here, right? StatKey runs that thing for me when I put it into StatKey and I show it. I can see that there are 600 samples, and I can see my standard error happening right here. Okay, we're running an alpha level at 5% on the problem. Okay, so when you run the p-value and when you actually do the p-value on this and you calculate it, the p-value comes out to be okay, and you can pull this up right inside of StatKey and you can run this test and see this. So the question becomes, would we reject based on a 5%? Well, yeah, the p-value is 0.0033, which is incredibly small, especially when in fact compared to the null hypothesis. So the answer would be yes, we would reject because the p was smaller than the alpha level. P was smaller than the alpha level. Sorry, this thing's jumping around. It's driving me crazy. Driving you crazy as well as it's driving me crazy. All right. Where am I? So we have a couple of things here, and I guess I don't see the question. Okay. Different samples in each case use the confidence interval to state a conclusion of the test that a sample and a given significance level are used. Okay. So I got this. We have a 95% confidence interval level between 6.3 and 8.7. Do we reject H of O? Don't we reject H of O? Okay. And at what confidence interval level talking about? Well, so first of all, if this is a 95%, then the alpha level is 5%. Okay. Our alpha level is always contrapositive of here. Okay. And remember, we're talking about a H sub O, right? We're talking about 0. And when we talk about 0, hold on one second. My computer just stopped on me. And I'm frozen for my figure. Hold on. Stay with me. Don't go anywhere. Okay, I'm back with you. So I was trying to get my computer working, and I couldn't get my computer working because my computer didn't print what belongs up here. So let's take a look at that. So the value that was given was 0.08. So if you take a look on your review, it'll show you that 0.8 is the p-value. And we were checking the hypothesis for not, so in the two tail. So let's go to the first one. And so first of all, this still stands that the significance level is 5% because of the 95. Look at the 0.8 and the p-value. Look at it inside of here. So we're testing this value. And since 0.8 is inside of here, we do not reject. If your null hypothesis is inside of your CI, then you don't reject because you take it for granted that it's inside here, belongs in here. 95%, again, I got a 5% significance level. 98 to 104, well, 0.8 is outside of this. I reject. And then my last one, 99% means I'm at a 1% alpha level. And I look at 0.8 and 0.76 to 0.94, it falls within there, I do not reject. So I'm not rejecting or not rejecting based on the alpha levels. I'm rejecting or not rejecting based on does the null fit inside of the CI that has been provided for me. All right, number 50, where are we? 51. So it says a certain species of trees have an average lifespan of 130 years. Rejector notices a large number of trees, specific Washington driftwood. She takes a core sample of 27 trees, count the number of rings measured in those rings. Counting the rings allows research to determine the age of each tree, and the average age of the tree sample is 120. So there's the average. The average age of the driftwood is less than, we're testing to see if it's less than 130. If the average age is less than 130, it might suggest that trees have died from unusual or invasive beetles or logging. So first of all, state the sample size. Well, the sample size are the 27 things that were measured. N is 27. State the sample statistic. Well, the measurement that we have are the rings that she counted, which were 120. So the sample statistic is 120. State the null and the alternative. Well, H sub O will be equal to 130, but H sub A will be less than 130. Okay, and this will be a mean value. So our statement would be mu is equal to 130. And for H sub A, mu is less than 130. H sub O, H sub A. X bar for the statistic. The direction of the tail. Well, the direction of the tail will be left because we're looking at something which is less. State the center of the randomized distribution. It'll be centered at the null, 130. Find the p-value for 0.8 and then write the conclusion at a 10%. Okay, so you're going to have to go up to stat key. You're going to have to run in there. You're going to have to actually go do that calculation. And you're going to have to find that number. That number will be smaller. It was smaller for me. And therefore, I wrote up that we reject the null. We have evidence that the average age of driftwood on the beach is less than 130 years old. Run your hypothesis test in StatKey using these parameters, and you will get an alpha value smaller than here if you tested it. But we can actually do it without even running the test if you want to, because the p-value is given at 0.08, which is less than an alpha level of 10. So if you want to test it, go ahead. But if not, it's just given for you here, and you can write it up. 52, the owner of a small pet supply store wants to open a store in another city, but he only wants to do so if more than 30%, right side tail test, households have pets. Otherwise, there won't be enough business. He samples 200, there's N, and he finds that 64 out of 200 have this. Okay? So first things first, state the null and the alternative hypothesis. All right, so what we're looking for is we're looking for 30%. So our null hypothesis, P, the proportion of people who own this cat or this animal, will be 30. If the H sub A is true, we want greater than 0.3. H sub O at the top, H sub A at the bottom. And you should label those. I just kind of don't have room. State the sample statistic. So in our sample statistic, we had 64 out of 200 people. 64 out of 200 people are my p-hat value. And 64 divided by 200 is 0.35. There's my statistic. B. Find the p-value from the randomized distribution below. Okay, so there's no numbers down here. So what do? So I look at my statistic and I go down here and I start to look at. So remember that my proportion was 0.35. Okay. Remember that I had 200 samples. Okay. And I'm measuring to see when that will happen. So I go to about right here, 0.350. That's my number, 0.350, 0.350. That's my data stat. And I start counting dots. Well, there's about 15 dots here. 15 dots as extreme or more extreme than my 350, okay? 15 dots divided by 200 dots will give me my percent of value happening off to the right-hand side. So if I take that, and I'm going to take my calculator and do the division, I get approximately 0.075. This is my p-value, my manually calculated, very rough estimate p-value. Then the question is, okay, remember that we were dealing with a 5% alpha level. So the question is this smaller than 5%? Well, if you move it over, this is 7.5%. This is 0.05. This is 0.075. The p-value is larger. So what is our decision? We do not reject the null. There is no evidence that the proportion who own pets in the city is more than 30%. That'll end it up for you for examination number 2 review. Practice, be prepared, be ready, and remember, it won't be that long before you see exam number 3, just to let you know, because that comes about pretty quickly. Been a great time. Enjoy yourself, and I'll see you in class.